Okay, so today we're going to talk about derivatives of the natural logarithm, or log base e. So if you used your calculator to substitute in y1 as the derivative of natural log of x and set up a table on your calculator to actually view the values in your table set, then you'll notice that the derivative comes back with 0 as an error. If with x is 1, the derivative is 1. If x is 2, the derivative is a half. If x is 3, the derivative is 1/3. If x is 4, the derivative is 1/4, etc. So you should notice that the derivative of natural log of x is 1 over the input value, as long as the input is greater than 0. Now the reason that that is true is because the natural log function does not exist to the left of the y-axis, and there's an asymptote actually at x equals 0. So we do get a derivative of 1 over x, which looks like this. However, we only get the part for x greater than 0. If you don't have a graph, you can't have a derivative or a set of slopes. So I couldn't say from here that the derivative of natural log at -1 is -1, because I don't even have a graph there in the first place. There is no derivative for the graph on the left-hand side. Okay. Now, because of the chain rule and what we have on the inside, the derivative of natural log of anything that is not plane x is still 1 over anything that's on the inside. But because of the chain rule, it also has to multiply by the derivative of the inside. So this is really just the chain rule. And I very often do this as u prime over u. Now the domain of the function, the input, still has to be the inside part greater than 0. The only way that we can avoid having a restriction is if we had the absolute value on the natural log, because the absolute value of natural log, the natural log of the absolute value rather, would allow us to have both sides, but we still could never do the natural log of 0, so we would still have the asymptote. So this function would have a derivative on both sides, 1 over x, without the restriction for the left-hand side. Mostly we deal only with this natural log absolute value when we're going backwards. So if we start with a two-sided 1 over x, we end up with a two-sided natural log as the original. But when we're dealing with just taking the derivative, we can do just this part. Okay, now, we're going to practice some to make sure everyone gets the concept and understands basically what the rules are saying. So for the first problem, we have a product. And so the derivative is the derivative of x squared, which is 2x. Keep the natural log of x, plus keep the x squared, and the derivative of natural log of x says to put what's inside on the bottom, which is x, and the derivative of x goes on top. So you would see this simplified out as x being factored out, 2 natural log of x, and since this simplifies to just be x, we would have plus 1. For the next problem, we just have the natural log, so the x squared minus 3 goes on the bottom, and the derivative goes on the top. So notice that there's no longer a natural log in this problem. So if we were looking at this particular problem, since we still have a natural log, the domain restriction is still there, that the inside of the natural log has to be greater than 0. However, if we look at number 2, we wouldn't necessarily notice from the derivative. From the derivative standpoint, x simply can't be plus or minus root 3. However, for the natural log standpoint, we have the domain that x squared minus 3 has to be strictly greater than 0. So we would get our zeros by saying that x is plus or minus root 3. But if we test the number line for our goal with negative root 3 and root 3, we would have positive, if we substitute into here, a negative value between these two numbers, and a positive value again. So our domain is actually restricted so that we only have negative infinity to negative root 3 and root 3 to infinity. So we don't actually get to just ignore the zeros. We have to ignore all the negative part as well. So this becomes much more important when you're trying to decide whether or not the function has a positive slope or negative slope. So you're not just going to consider the derivative, but you also have to look at the restrictions for the domain so that you're not trying to tell us that there are values that are maxes or mins when there's no function graph in the first place. For the next problem, the derivative for natural logs is to take whatever is inside, and the derivative of that goes on top. For problem 4, I would rewrite this problem as natural log of x to the 1/2, and I would use log rules to bring this 1/2 down to the front so that my y value is actually 1/2 natural log of x. So my derivative is 1/2 times the derivative of natural log of x, which is 1 over x. So my final answer would be 1 over 2x. So I would rewrite problem 5 as x times, the power would come down, 2 natural log of x. So I still have a product, but I have a much easier product to do. So the derivative is the derivative of 2x. Keep the natural log, plus keep the 2x, and the derivative of natural log is 1 over x. So now my derivative is 2 natural log of x plus 2, or 2 parentheses natural log of x plus 1. For 6 and 7, there's no way to simplify this. I'm going to have to do the quotient rule. So the derivative is low d high minus high d low over the square of what's below. So at least once this simplifies, we no longer have a complex fraction to deal with. So that's nice. Similarly, number 7, using the quotient rule, is low d high minus high d low over the square of what's below. So again, simplifying, we don't have to deal with the complex fraction. Now, on this one, I wanted to do this one to point out, you cannot cancel any of those natural logs. If something doesn't factor, it does not cancel. So no factor, no cancel. So I can't cancel anything in that problem. Now this problem number 8 is different from the initial problem number 4. Notice here the power is on the x, not on the entire natural log. This is a very different problem. So we cannot bring the 5 down. This has to be done with the chain rule. So y prime is the power derivative, which is 5 natural log of x to the 4th, times the derivative of the inside, which is 1 over x. So our derivative would be 5 natural log 4 of x. And you'll see that notation, but I'm not a very big fan of that because it tends to run together. So I'd rather you leave them like this. Here. Okay, so this problem is very much like the last one that we just did. It's the entire natural log to the half. So we have to do the chain rule. So y prime is 1/2 natural log of x to the negative half. So we've done the power, times the derivative of the inside. So this one, when we simplify out, technically the 2 is on the bottom. We have an x on the bottom, but this square root is a negative power also goes on the bottom, leaving us just 1 on top. Okay. Now remember, you have to do this problem very much like you did number 9. It's the chain rule because natural log doesn't have a power on it. So we have the derivative of cosine, which is negative sine, keep the guts, times the derivative of the inside. So we would have negative sine of natural log of x all over x. Okay, 11 is completely different. This is natural log of anything. So this is like natural log of u. So our derivative says to take 1 over whatever is inside and put the derivative of what's inside on the top. So it's going to be u prime over u. They would not leave it this way on a multiple choice. It would be rewritten as negative, and sine over cosine is tangent. Now, more people miss this type of question than any of the others because the natural log has the natural log inside. But remember, this is really just our u. So the derivative is u prime over u. So the u goes on bottom, natural log of x, and the derivative of u, 1 over x, goes on top. So simplified out, this would be 1 over x times natural log of x. Okay, now log rules. We talked about these just briefly on the previous page, so I've got to remind you of what's really important on here. So I'm going to move my page down and make a little extra space. Okay, so here, what you want to remember is that you can do a product, comes out. You can do a quotient that comes out. And the power can come down. But that only works if these are inside. So there is absolutely no way to simplify log of a plus or minus b. So there's no way to do that one. There is no way to simplify log of a times log of b. There is no way to simplify log of a divided by log of b. And there is no way that you're going to simplify log of a all raised to a power. That's a chain. So there's no simplification for that. Okay, so I'm going to show you why it's so important to know your log rules. I'm going to do the first 2 problems, both the hard way and the easy way, so that you can decide for yourself. Okay, so the derivative says to take whatever is on the inside and put that on the bottom. And the derivative of the inside goes on the top. But the derivative is 1/2 x squared plus 2x minus 3 to the negative half with the chain rule involved. So the derivative of what's inside the logarithm is the derivative of this entire part here. So it's all of this is the derivative of the bottom. So this is u prime over u. So to get that simplified out, I could, on here, move this power down. So I have 1/2 of 2x plus 2 on top. And then I have 2 square roots on the bottom, but they're identical square roots. So that means that my derivative, 1/2 of 2x plus 2, is just x plus 1. And the square roots cancel, and I end up with x squared plus 2x minus 3. Okay. Instead of doing that, I would use log rules to bring this power to the front and rewrite first. So notice, I cannot do anything with addition and subtraction. So this is the best that I can simplify. But now my derivative is 1/2 u prime over u, which is now u prime over u. So x plus 1 over x squared plus 2x minus 3. So it's much easier algebraically. Okay. I'll zoom in a little to the next problem. So on this one, the hard way would be to do the product rule. So the derivative says it's u prime over u. So I'm going to put my u on bottom. And the derivative of the top is a product. So it's 2x derivative, keep e to the x, keep the x squared, and the derivative of e is e. But we're not done. We have to simplify. So we would factor out an x and an e to the x from the top. leaving behind a 2 plus x. On the bottom, I also have an x and another x and an easy x. So canceling, I'm left with y prime equals 2 plus x over x, or 2 over x plus 1. Now this is actually the preferred format because now I can see exactly where the function is undefined and where the function would be 0, or where the derivative would be 0 rather. Now the easier way would have been to use log rules of the product to rewrite so that this is the natural log of x squared plus the natural log of e to the x. I can further simplify by bringing the power down so that this is 2 natural log of x plus natural log and e cancel, so just plus x. So now, after I do my rewrite, I can do the derivative is 2 times the derivative of natural log plus the derivative of x. So we get the 2 over x plus 1 much easier with less algebra. So worst case scenario, you would have to find a common denominator. And 1 could be written as x over x. So again, we have 2 plus x all over x. So much easier way to get your answer. So whenever we can, we're going to use log rules to simplify. So for this problem, I would rewrite as 2 natural log of x. So just bringing the power down so that my derivative is just 2 times the derivative of natural log, which is 1 over x, so 2 over x. Okay, for this one, just as a side note, if I were to try to do this the hard way, I would have my derivative as the entire u goes on the bottom, and I would have to do the quotient rule on top for the derivative of this. So let's not do that. And plus, you would then have to simplify that algebraically. Let's not. Instead, we're going to rewrite this using the subtraction rule for logarithms that says this is equivalent to natural log of x squared minus natural log of 3x minus 2. I'm further going to simplify by bringing the 2 down so that I have 2 natural log of x minus natural log of 3x minus 2. So now my derivative is 2 times 1 over x minus the u goes on bottom and the derivative goes on top. So without ever having to do a quotient rule, we have a very nice derivative. Okay, so for this next question, we're going to use our log rules again. So we're going to avoid the product rule and the chain rule. We have a half power, but only on the second part. So we're going to use the fact that this is a product to split into natural log of x plus, now the second part is the natural log of 3x minus 1 to the half power. And we can bring the power down. So we can really do that step all at one time as long as we're careful. So now our derivative is the derivative of natural log of x, which is 1 over x, plus 1 half the derivative of natural log of 3x minus 1. Remember, we're using the u prime over u whenever we do the derivative of natural log. So it's not really just 1 over x. Technically, it's x and the derivative of x. So it's 3x minus 1 and the derivative, which is 3. So for the next question, this time we have a quotient. So that means our natural log is going to be subtracted. But both parts have the half power. So it's 1 half natural log of x squared plus 1 minus 1 half the natural log of x squared minus 1. So my derivative, okay, so again, just as a reminder, we both have the half power, so the top and the bottom. And because it's dividing, we subtract. So our derivative says to hold the half x squared plus 1 goes on the bottom, and the derivative goes on top. Hold the negative half. The x squared minus 1 goes on the bottom, and the derivative goes on top. So you would see this simplified because the half will cancel the 2's, so that it's just going to be x over x squared plus 1 minus x over x squared minus 1. Okay, so this again is the prime example of why we would not want to have to do this the hard way. This would be the entire thing on the bottom, which would make this whole thing my u. And then the entire derivative of that, which is a product with a quotient rule. So it would be low derivative of the high product minus high derivative of the low chain rule over the square of the bottom, which would make it to the 2/3 power. And we would have to try to simplify all of that out. So we don't want to have to do that. Okay, what we'd rather do instead is use our log rules. It says that we have the natural log of x on top plus 3 because of the power coming down, natural log of x squared plus 3 minus, there's a 1/3 power really on the bottom that's going to come out to the front of the natural log 2x squared plus 4. So what we have to be careful about is the x does not have a power, so it should not have anything in front. The x squared plus 3 does have a power, so it has a 3 in front. Similarly here, and it's top minus bottom. So our derivative now is the derivative of natural log plus 3 times the fraction, x squared plus 3 on bottom, 2x on top, minus 1/3 times the fraction, 2x squared plus 4 on bottom, 4x on top. Now, worst case scenario, they distribute the 3 and distribute the negative 1/3, but usually you could just leave it factored out. Okay, now, on to some implicit derivatives. Okay, so it works the same way that it always has. So the derivative of x squared is 2x. Keep the negative 3. The derivative of natural log of x is normally 1 over x. So the derivative of natural log of y is 1 over y, but we have the implicit dy dx. Plus 2y, and again the implicit dy dx, equals 0. Now, in deciding which way that I move, if I move the 2x over, I'm going to get an additional negative. If I move the dy's over, I'll have one negative, but the other will be positive. Remember, we want to minimize the number of negatives. So I'm going to keep the 2x. I'm going to move this over so that it's 3 over y becomes positive. And a 2y is now going to become negative when it moves over. And I'm going to go ahead and factor out the dy. So moving over, I have 3 over y becomes positive times dy, and negative 2y times dy. So now what you'll never see left on a test, if you ever have a multiple choice question or a question on the free response that says, show that dy dx equals this fraction, you will never have a complex fraction. So we're not going to have a fraction on top of a fraction. That means it's in my best interest to multiply both sides by y before we go on. So that means that 2xy equals 3, and the y's cancel, minus 2y squared, and we still have the dy dx. So now, 2xy divided by 3 minus 2y squared equals dy dx. Okay, I'm going to zoom out a little. This next question asks us to find the equation of the tangent line at this point. So I have the point, I just need to get the slope, so I'm going to do the derivative. Get 8x minus the derivative of natural log of x is 1 over x. So that derivative at x equals 1 is 8 minus 1, which is 7. So my equation of the tangent line, which I don't simplify, is y minus 4 equals 7x minus 1. Okay, now we have 7 basic rules for derivatives: power, product, quotient. There are 6 trig ones. inside the basic rules. The inverse trig, which we have 3, but really 2 that we use most often, which is sine inverse and tangent inverse. Now we have e, and we've added on natural log. So let's go through these together. This one requires a chain rule. So the derivative of the outside is 2 e to the x plus 3 to the first power times the derivative of the inside, so times e to the x. So you would see this written as 2 e to the x times e to the x plus 3. Remember, we prefer factored, not FOILed, not distributed. Okay, this next one is a product. So our derivative is derivative of x, keep the e, plus keep the x, derivative of e, which is himself. We prefer factored, so we'll pull out e to the x and leave behind 1 plus x. The next one is also a chain rule. So the derivative of sine is cosine, and we never change the angle, never change the insides, times the derivative of e to the x, which is e to the x. Number 4 is also really a chain. It's the derivative. E to the x stays, times the derivative of the inside, which would be cosine x. And remember, we typically see these written with u prime, e to the u. We don't want the power to run into the derivative that's not part of the power. Okay, for this one, just as a reminder, we cannot separate plus and minus inside of a log. Inside of a log, we can do power, product, quotient, only if they're inside the logarithm. So that means that on this one, I have u on bottom and the derivative on top. So remember, this format is really u prime over u. We cannot simplify number 6. We have to do a quotient rule. So y prime is low d high minus high d low over the square of what's below. So you would see this in factored form. So you would see the e to the 4x pulled out. That leaves behind 4x minus 1 all over x squared. And the reason you see it that way is because, remember, e is never negative or 0. So our only 0 can come from this value, and our only undefined spot can come from x being 0. So that would be our horizontal and vertical slopes. So if we do the same thing in the other direction, we have to be careful with our low d high. Order does matter. So it's low d high minus high d low over the square of what's below. So my y prime gives me e to the 4x factored out, 1 minus 4x. And technically on the bottom, I have e to the 4x times e to the 4x. So one of these is going to cancel. So my final y prime is 1 minus 4x all over e to the 4x. Number 8 is something that we would prefer to have simplified. So you have to think about this as the cube root of e. It's not the cube root of x, it's the cube root of e. So it's e to the 1/3 for the x. So my derivative says keep the e times the derivative of the power. But you would probably see this rewritten as 1/3. And remember, this was what we kept. So really, you might see it written this way, but you might see them put it back as the cube root of e to the x. Okay, number 9, we can definitely simplify. We can pull the 6 down because the 6 is on the x, and rewrite this as 6 natural log of x. So the derivative is 6 over x. For number 10, we have exactly u prime over u. There's no simplification for plus and minus. So x squared minus 5x minus 2 goes on the bottom, and 2x minus 5 goes on top. Number 11 has to be a chain rule because it's not inside the natural log. So the power comes down, natural log of x to the 6th times the derivative of the inside. So you could see this as 7 natural log of the 6th over x, or maybe even 7 over x in front. Okay, now this x cubed cannot be fixed because the power is not with the inside the natural log. So we're just going to have to do a product rule. So derivative of the first, keep the second, keep the first, derivative of the second. So your derivative is going to have 3x squared, natural log of x, plus x squared. You would see this most likely factored out. So it's 3 natural log of x plus 1, all times x squared. Okay, for number 13, I have the quotient rule. So we have low d high minus high d low over the square of what's below. So our derivative is going to be 4x cubed natural log of x minus x cubed all over natural log of x squared. And again, you would probably see this factored out. So it would be x cubed parentheses 4 natural log of x minus 1 all over natural log of x squared. So remember, this absolutely cannot cancel. If it doesn't factor out, it cannot cancel. So now our derivative is low d high minus high d low over the square of what's below. So I would have to factor out again. So this would cancel and make x cubed, but I would still have to factor out the x cubed. And that would leave me with 1 minus 4 natural log of x all over, and this is really x to the 4th times x to the 4th, so x to the 8th. This would still simplify because the x cubed and x8 are factored out, so they can cancel, and leave me with x to the 5 on bottom. For number 15, our derivative is 2x minus hold the 4, and then 1 over x. So the derivative is 2x minus 4 over x. So if you had to find a common denominator, you would then want to multiply by x over x, so that we would have 2x squared over x minus 4 over x. You would probably see the 2 factored out and have x squared minus 2 in parentheses all over x. Okay, so again, this last problem on this page is one that people struggle with because the natural log is inside. So remember, think of that more as your u. So if your u is natural log of 3x squared, we could rewrite that as natural log of 3 plus 2 natural log of x. So we're doing the product, so the product inside can be split up, and this is a power. So that means that our u prime would be 0 plus 2 over x, because natural log of 3 is actually a constant. So if we do the derivative of natural log of u, the derivative is u prime over u, which is 2 over x over natural log of 3x squared, which we would see as 2 over x natural log of 3x squared. Okay, so the derivative of natural log of sine x, the derivative of y equals natural log of sine x uses the u prime over u format. So the sine x goes onto the bottom. Okay, hold one second. I'm going to have to reorient my software. Pause. Okay, we're back. So the derivative is u prime over u, as we said before. And so it's going to be sine of x, and the derivative of sine would be cosine. So you would see this rewritten as cotangent of x. Now number 18, using the chain rule, the outside this time is not natural log. So the derivative of sine is cosine. Keep the angle times the derivative of the inside, which is 1 over x. So you would see this simplified just to put the x underneath, like so. For number 19, we have a product rule. So the derivative is the derivative of x. Keep the natural log of tangent x, plus x times the derivative of natural log tangent, which is the u prime over u format. So tangent x goes on the bottom, secant squared x is on top. So this really doesn't simplify nicely. We still have natural log of tangent x plus x. So we could put the x and the secant squared as one fraction. So x secant squared x all over tangent x. Okay, so for this one, this is not one of our log rules. You can only do log rules for what's inside of our logarithm. So we're going to actually do the quotient rule. So we have low d high minus high d low over the square of what's below. Now on this one, you would find that they would make a common denominator. So since the tangent, which is a function in and of itself, cannot cancel with the function 1 over x, we would have to multiply the first term by x over x, so that we would have y prime equals x natural log of x secant squared of x minus 1 over x tangent x, this x. So basically we end up with a common denominator where the x's belong on the bottom with the natural log. So what we would see is both the x and the natural log of x quantity squared on the bottom. Okay, so both this x and this x came down. Now, be careful about this. If you write natural log of x and then square, that is implying the x is squared, which is not the same thing. You absolutely need to keep your parentheses. For number 21, we have a product inside of a logarithm, so we can split this one before we start. Natural log of 3x squared minus 3x plus 2. It does need parentheses because all of it should be inside the log, plus the natural log parentheses of 5x minus 1. We cannot split anything else inside. We can only split the inside product, inside quotient, or inside power. So now our derivative is u prime over u. The derivative is u prime over u. The only difference between number 21 and number 22 is that instead of adding for the product, we subtract for the quotient. So our derivative looks exactly the same. It's still u prime over u. But there's a minus in between this time for the next u prime over u. For 23, we would rewrite this so that it shows that the inside of the log has a half power, not the outside like up above, the inside. So now we could rewrite and bring the half to the front. So now our derivative is 1/2 of u prime over u. So 2x minus 4 over x squared minus 4x minus 7. Now for this one, since this half can factor and cancel, okay, remember we never cancel unless something factors. I could factor a 2 from the top, and we already have a 2 factored out on the bottom. That's the only reason that we can cancel. No factoring, no canceling. So if something doesn't factor, you have to leave it. So we can simplify out. So for number 24, we're going to rewrite this as the 1/5 power on the inside. So our derivative is, well, let's rewrite first so everybody's following along. Our rewrite is 1/5 natural log of 3x cubed minus 2x squared plus 5x minus 1. Remember, there's nothing we can do about plus or minus. So now our derivative is 1/5 u prime. So 9x squared minus 4x plus 5 over u. For number 25, this is really the top part has a square root and the bottom part has a square root. Since everything has a square root taken, we can actually split that up. But this is all inside, so we can rewrite this as 1/2 natural log parentheses 2x minus 1 minus 1/2 natural log parentheses 2x plus 1. So now our derivative is to hold the half, u prime over u. Hold the negative half, u prime over u. So we can factor this out here. It does cancel. So our derivative is 1 over 2x minus 1 minus 1 over 2x plus 1. Okay, now 26 again is a perfect example of where all of this would belong on the denominator. And the derivative of this, which is a product, chain, quotient, all blended together, would have to be done on the top and then simplify. So instead, we're going to rewrite the natural log x to the first power, so that's just plain natural log of x, plus the 1/3 power for natural log of 2x minus 1, minus, because on the denominator, we have 1/3 power natural log of 2x plus 1. So our derivative is u prime over u plus 1/3 u prime over u minus 1/3 u prime over u. Since nothing cancels, I'm just going to leave it that way. Okay, some more of the practice with implicit. The derivative of 4x squared is 8x, plus 2, the derivative of natural log is 1 over y dy dx, plus 3y squared dy dx equals 0. So I'm going to get rid, anytime we have a fraction with the dy, we need to get rid of that. So I'm going to multiply everything by y. So now we have 8xy plus 2 dy plus 3y cubed dy equals 0. So now I'm going to factor out the dy on the left-hand side, and that belongs with 2 plus 3y cubed. And I'm going to move the 8xy over, so it's going to become negative 8xy. So now we have dy over dx is negative 8xy over 2 plus 3y cubed. Our next problem has a product in the middle, so we're going to use our log rules to simplify first. So the natural log of x plus the natural log of y minus 3x equals 4. So first we're just doing our rewrite. Now we're going to do our derivative. 1 over x plus 1 over y dy minus 3 equals 0. So again, when we have a fraction with the dy, we really need to fix that. So I'm going to multiply everything by y. So I have y over x plus dy minus 3y equals 0. So dy dx equals 3y minus y over x. So worst case scenario, if you had to find a common denominator, this would be 3xy over x minus y over x. So 3xy minus y all over x. Okay, for the next one, we could do the product rule or the quotient rule. Some people prefer the product, so I'm going to multiply both sides by x to do a rewrite. And so my rewrite is that the natural log of y equals x squared plus xy. So now the derivative is 1 over y dy equals 2x plus a product instead of a quotient. So the derivative of x, keep the y, keep the x, derivative of y. Since we have a fraction with our dy, we need to multiply everything by y. So we'll now have dy dx equals 2xy plus y squared plus xy dy dx. I'm going to subtract this term over and factor out the dy. So the dy on the left, there's one dy on the left, minus an xy dy that's coming over, leaves me with 2xy plus y squared. So my dy dx is equal to 2xy plus y squared all over 1 minus xy. Okay, for the next part, we cannot split plus inside of natural log, only power, product, and quotient inside. So that means I have the derivative du, 1 plus dy, over x plus y equals, remember the formula for arctangent is 1 over 1 plus the inside squared times the chain rule, which is a product that needs parentheses. Every time you do the product rule times something, it has to have parentheses. So 1 times y plus x times dy. Now we are not going to simplify because you wouldn't be expected to simplify something that's complicated. Usually you just sub in from here. Okay, the last three problems, which I realize on mine are misnumbered. 31, 32, 33. Okay, find the equation of the line tangent to the graph of the following functions. So we already have a point for each function. So for each one, we're really just looking for the slope. So y prime is negative 4x plus 1 over x. Y prime at 1 is negative 4 plus 1, negative 3. So y minus negative 3 equals m x minus 1. For the next one, y prime is negative 2x minus u prime over u. So u prime is 2, u is 2x plus 1. So the derivative at 0 is 0 minus 2 over 0 plus 1.